Have you ever wondered why most factories, transmission lines, and industrial motors use three-phase power, whilst most residential homes use single-phase power? In today's video, we are going to go through what three-phase power is. So now, from the term three-phase power, let's single out a phase. So what is a phase? So a phase refers to a single sinusoidal AC wave. So as you can see here, this is a phase. So this graph here shows the increase in the voltage of the phase with respect to time. So now, knowing that a phase is a single sinusoidal AC wave, three phase is simply having three individual phases together of identical frequency, identical amplitude or size, joined together or combined together at an angle of 120 degrees apart. So simply, as you can see here, you have a single phase or just a phase A, you have another phase B, you have another phase C. So these phases are individual phases combined together to give us a single phase. But remember keenly, these phases are separated at an angle of 120 degrees apart. So now, find the voltage of each of these phases. Example, VA, the voltage of VA would be equal to the maximum voltage of VA, which is this point, let's say VM sine of bracket open omega t. So our omega t here is just the position of or the angle of the wave with respect to a particular time. So now we know that omega is equal to angular frequency, and frequency F refers to the number of complete cycles per second. So now, if we say omega t, we are talking about the angle of the wave at a particular time. So now this plus 0 degrees. This 0 degrees. So first we are talking about phase A. So it will be plus 0 degrees. That's right. This is phase A. Phase A. 0 degrees. Then phase B, or the velocity, the voltage of phase B will be equal to Vm, which is the maximum voltage of phase B to phase B. So this was phase A, then this is phase B. So let's say MA, and let's say MB. So now the maximum voltage, of phase B, which is this sine of bracket open omega t, then minus an angle of 120 degrees. So there's a decrease in the angle, the angle separated apart from the 0 degrees reference. So now we'll have, then the last one, VC, equals to Vm sine of omega t plus of 120 degrees. So remember, mathematically, plus of 120 degrees is the same as minus 240 degrees when you check on the circle. So now with this, basically, the most important thing is that each face has to be separated by an angle of 120 degrees. So our 0 degrees here for face, the face A here was our reference, having an angle of 0 degrees. Face B had an angle of minus 120 degrees, like a decrease, and face C an increasing angle, positive 120 degrees. So now with this, let's move to why three-phase power and not single how three-phase power is produced. So now three-phase power produces a constant or steady power. Constant or steady power. The single phase produces pulsating. So that is to say that over here we had, so from 0 power increases. So power increases because voltage and current increases. So at this point we'll have maximum power produced. Remember, power P is equal to IV. So as current and voltage increases to this point, we have a maximum power produced at this point. Then it decreases again to this point. So that increase and decrease is what we refer to as pulsating. So remember, when it also decreases to this point, when it also decreases to this point or this point, we would be having power being produced because we would have a negative voltage, like negative voltage multiplied by a negative current. So this gives us power. But now the main reason here is that increase in power produced to a 0 power produced, then back to power being produced again. That results in the word pulsating power. So the power is not constant. But with the three phase, as you can see here, considering this point where this phase is reducing or decreasing, there's another phase also increasing. So now the total power produced by the three phase here is equal to the power produced by phase A plus power produced by phase B plus power produced by phase C. So now this results in constant power because when one is reducing, the other is increasing. At this point, where both this phase and this phase were reducing, this phase was producing a maximum power. Same as this point where this phase and this phase was reducing, this phase was also producing the maximum power. So now with these all added together, you have a constant power supply at all times, unlike the single phase. So now another advantage of the three-phase power over the single-phase power is that to transfer a given amount of power, let's say P, you would require 25% less copper when using the three-phase system as compared to the single-phase system. So that is to say that in buying less copper, that means less expense, while you are still being able to achieve the same cost or transfer the same power. So now with these two advantages, the last advantage of the three-phase power over single-phase power is that You can always connect a phase, a particular phase in a three phase in addition to a neutral point to form a single phase. So you can always create a single phase from a three phase. So it's kind of like three phase is the set and main set, then single phase is the subset. So you can always get a single phase from a three phase. Now, with this, let's move into how three-phase power is produced. So now, basically, three-phase power is produced by using an alternator. So what you have here is a cross section of an alternator, which we'll talk about. But what is an alternator? An alternator refers to a synchronous generator. You all know a generator is a device that converts mechanical energy to electrical energy. So it converts a particular motion into electrical energy. So with this, our alternator, we have a stationary part and a rotating part. So our rotating part here is the rotor, and our stationary part here is the stator. So now our rotor here can either be an electromagnet or excited DC windings. And on our stator, you have three coils. So you have three copper coils on the stator. These copper coils are separated at an angle of 120 degrees apart. So over here, this is a coil. So A is one of the coils, B is one of the coils, and C is one of the coils. The B prime, B prime, A prime, and C prime are the internal parts of these coils, while the A, B, and C are the external parts of the coils. So now, with this rotating stator and stationary conductors A, B, and C, with reference to Faraday's law, of electromagnetic induction, it says that when you have a relative motion between a conductor and a changing magnetic field, you have an EMF induced on the conductor. So now that is to say that we have EMF induced on A, B, and C, which are the conductors. Then this power is now transported to an external circuit through the stator. So basically, this is the flow of how AC, three-phase AC power is generated. So now, let's go forward to look at how we connect these phases in practical power systems. That is the Y and the delta configuration. So now, let's talk about the Y connection. So in the Y connection, you have each phase connected to a single load. So now these three phases all meet at a central point called the start point. Then from this central point, you have another connection line back to the source. So this connection line can either be used as the neutral line, or for the purpose of grounding. Now, this connection I outlined here, we are supposed to have our load being connected to B, because initially we said B, A, and C. So B, A, and C are our external parts of the core, and the connection is done through the external part. So it's supposed to be from B then to the load. So now with this, let's look at what the the voltage relation in the Y configuration. So now in the Y configuration, first let's know what VL. So VL, which is the line voltage, refers to the voltage between two phases without a neutral. And our phase voltage VP refers to the voltage between the phase and a neutral. So now in the Y configuration, our phase voltage or our line voltage VL is equals to root of 3 times the phase voltage VP. VP. So this root of 3 comes from the 120 degrees separation of the cores. And our line current IL is equals to our phase current. So now our line current IL simply refers to the current moving from our source to our load. And as you can see here, each line directly feeds the load. So our line current, the current flowing through the line is the same as the current flowing through the phase for the Y connection. So now, because of the availability of this neutral line in the Y connection, the Y connection is mostly used for distribution purposes. And not only that, but the Y connection also produces a much lower phase voltage than the delta connection. Now with this, let's move to what the delta connection is. So now for the delta configuration, each phase is connected end to end. You have two phases meeting at each end. So you have this phase, let's say phase A and phase B connected end to end. So now in the delta configuration, the line voltage VL, which we said refers to the voltage between two phases, is equals to our phase voltage VP. This is because our load here is connected across two phases. So this is one of the phase and this is the other phase. So if you measure the voltage between this phase and this phase, would be the same as the voltage passing through this load, which will determine our phase voltage. So in the delta configuration, phase voltage is equal to our line voltage, and our phase current, our line current IL, is equal to root of 3 times the phase current I. So that is, the line current is greater than the phase current. So now, this is because each line feeds two phases. So you have a single line feeding two phases. So now, because the delta configuration usually produces balanced power, it's used for three-phase industrial motors or equipment. So now with this, we'll move to the differences between the delta configuration and the Y configuration. In the Y configuration, we have three phases connected together at a start point, then a neutral from the start point back to the source. That is in terms of connection. Then for the delta configuration, we also have three phases connected end to end. Then in terms of the shape, we have our Y configuration, as the name implies, to have a Y shape where this point is the neutral point, then these ones are the output to our source. Then for the delta configuration, we have a delta shape, that is a change shape or a triangular shape. So now, in terms of the number of wires, the Y configuration has 4 wires in total. That is the three phase wires and the neutral wire. Whilst the delta configuration has three phase wires only. So three individual phase wires only. Then in terms of voltages, as we said, for the Y configuration, VL, the line voltage, is equals to root of 3 times the phase voltage VP. And this is because, as we said earlier, this phase voltage is only across the core. So the phase voltage is only across one core, while the line voltage spans across two cores. Hence, the root of 3 difference. Then for our delta configuration, we also said that VL is equals to VP. So this is because each load is connected directly to the junction of two phases. Hence, the live voltage, which is the voltage from between the two phases, and the phase voltage are the same. Then, in terms of current, IL, which is our line current, is equals to our phase current. Because from the connection, you could see that it was just a single wire in the Y configuration connecting the source to the load. So that single wire is the line wire and at the same time the phase wire. So hence our line current is equals to our phase current. All in all, it's because of the series circuit or series connection between the load and our source that give us this IL equals to IP. And now in our delta configuration, IL is equals to root of 3 multiplied by IP. So now this root of 3 here comes from the angular dislocation, that 120 degrees angular dislocation of the faces. And now with this, let's now move to the last part of the video, which is we trying to know how power from our generation station gets to our homes. So now the diagram we have here shows the individual stages involved. So here is our generator. So this generator here is the alternator. Then the voltages generated at the alternator are usually less voltages. So it's stepped up using a step up transformer to higher voltages so that it can be transferred without increasing the losses. Now remember that power is equals to VI. So in transferring a given amount of power, increasing the voltage means decreasing the current. So that is to say that so V is equals to P over I. So increasing the voltage means decreasing the current. And current here is what increases the copper losses. So simply in transferring, in order to reduce the losses in the transmission, voltage is stepped up. Then when this stepped up voltage is transferred, it goes to our primary stations. So at the primary station, it stepped down and further stepped down again at the secondary stations, then stepped down to our neighboring pole-mounted transformers, which are the PMTs, or the ground-mounted transformers, which then supply power to our homes. So now, I've also made a video explaining how this three-phase power is connected in our transformers. That is, I've made a video on transformer vector groups. So the link is in my description box. Kindly click on it and learn more about transformer vector groups. It's simply explained to the most simplest level you can ever think of. And if you found this video helpful, if you've learned a new thing, kindly hit the like button for the purpose of YouTube algorithm, and also subscribe for more electrical content. Thank you.